Hello and welcome to the January 2015 Regents exam in chemistry. This is a walkthrough of part B-1 and you are now looking at question number 31. Question number 31. What is the number of electrons in an aluminum plus 3 ion? Note that the charge of this ion is plus 3. I've included some information from the periodic table, the box that has aluminum in it, and we can always tell from the boxes on the periodic table the number of protons, which is the atomic number, in this case 13, and if the atom was neutral it would also have 13 electrons. But now we're dealing with an aluminum ion with a plus 3 charge, meaning it has lost 3 of its electrons, so the electron number has been reduced to 10. And now you can see why the charge is plus 3, because the electrons are negative, protons are positive, and if you add 13 to negative 10 you get positive 3. And that brings us back to our answer, and the answer is number 1, 10 electrons. Question 32. The valence electron of which atom in the ground state has the greatest amount of energy? We're given 4 choices: cesium, lithium, rubidium, and sodium. Let's locate them on the periodic table. They're all members of the same group, which is group number 1, which means they all have 1 valence electron. You can see that in their electron configuration codes. But you notice the difference as we go down through the periodic table. That 1 valence electron is further and further away from the nucleus. In fact, cesium, the valence electron is in the 6th energy level. That's the furthest from the nucleus. Now from basic atomic structure, remember that electrons located further from the nucleus generally have more energy. So our winner is going to be cesium. That's going to be answer number 1. We'll come back and enter answer number 1. Question 33. The numbers of protons and neutrons in each of 4 different atoms are shown in the table below, and they've given you this nice table. And we have atoms A, D, E, and G. You can see the numbers of protons listed and the numbers of neutrons are listed. Question is, which 2 atoms represent isotopes of the same element? From our understanding of isotopes, we know that we're looking for 2 atoms of the same element, and they must have the same number of protons. They'll also have different numbers of neutrons. That's what makes them isotopes. So we'll come back to the available answers. You notice these 2 elements, D and E, have the same number of protons, so they're going to be our choice. D and E would be selection number 3. Our answer to question 33 is 3. Question 34. Which elements have the most similar chemical properties? We're given various pairs of atoms here, and we're asked which pair of elements is going to have the most similar chemical properties. Well, hopefully you recall from your study of the periodic table that elements found in the same group on the periodic table are going to have the closest similarity in their chemical properties due to their electron configurations. So we're looking for a pair of atoms that occupy the same column on the periodic table. I've imported a small periodic table for us to analyze here, and we'll look through the various pairs. The first pair is boron and carbon. Here's boron and carbon. They're located in the same row, but not the same column. Next is oxygen and sulfur. Oxygen and sulfur, they look good. They are located actually in the same column. So they're going to be our choice. That's going to be our answer. But let's eliminate the other ones first. Aluminum and bromine. Here's aluminum, here's bromine. Not only are they not in the same column, they're not even in the same row. Argon and silicon. Here's argon, silicon back here. They're in the same row but not the same column. So the only pair of elements that share the same column here are going to be selection 2, oxygen and sulfur. So we're going to answer 2 and move on to the next question. Question 35. Which element reacts with oxygen to form ionic bonds? 2 ways to go about this question. I'll do it the hard way first, and then we'll show you the shortcut. The 4 elements that we're supposed to compare to oxygen are calcium, hydrogen, chlorine, and nitrogen. Whichever of these elements generates the greatest difference in electronegativity when compared to oxygen will be the one that's most likely to be ionic. Since oxygen has an electronegativity of 3.4, we only need to look up the electronegativities of our 4 potential candidates here to find out which one is going to give us the biggest difference. So we're looking for the smallest electronegativity. I've included the reference table section that gives us electronegativities. This comes from table S, and I've highlighted in yellow the electronegativities of the 4 elements in question. The smallest of these 4 values comes from calcium, and that's a 1.0, so our electronegativity difference would be 2.4. That's well above the threshold, which is typically 1.7, which would make this an ionic bond. So our answer is going to be calcium, answer number 1. The shortcut would be simply to notice that calcium is the only true metal among these 4 atoms, and when you combine a metal with a nonmetal, such as oxygen, you are likely to form an ionic bond. Question 36. The table below gives the atomic mass and the abundance of the 2 naturally occurring isotopes of chlorine. Here they are, chlorine 35 and chlorine 37. We've listed the atomic mass values of each. Here they are. And the natural abundances in percentages of 75.76 and 24.24. Which numerical setup can be used to calculate the atomic mass of the element chlorine? This is a weighted average determination. And when you do a weighted average, what you're going to be doing here is multiplying the independent weights of the isotopes by their natural abundances, which are percent values. Key to the question is understanding that the natural abundance values, the 75.76, which goes with the 34.97 mass, has to be converted into a decimal equivalent before you do the calculation. So that's going to be 0.7576. And we multiply those 2 values together, and we're going to be adding the product of the second mass multiplied by its abundance. Its abundance is 24.24%, which converts to 0.2424. This statement should be one of the potential answers, and let's see which one it is. We see that one is answer number 3. So our answer is number 3. This is how we compute the weighted average, which gives us the average atomic mass, in this case for the element chlorine. Question 37. Which general trends in first ionization energy and electronegativity values are demonstrated by group 15 elements as they are considered in order from top to bottom? To help with this question, I've cut out a small piece of the periodic table and indicated the 3 elements in question here of group 15. And we've looked up the values from table S that correspond to this particular question for the nitrogen, for the arsenic, and for the bismuth. You can see the ionization energy as you go from top to bottom, nitrogen to bismuth. The numbers go from 1402 down to 703. That's a decrease. And electronegativity values start at 3 and go down to 2.0. That's also a decrease. So we're looking for an answer where the first ionization energy decreases and the electronegativity also decreases. That's going to be answer number 1. Question 38. An aluminum sample has a mass of 80.01 grams and a density of 2.70 grams per cubic centimeter. According to the data, to what number of significant figures should the calculated volume of the aluminum sample be expressed? Here we're not as much concerned about the science of what's going on as we are about the technique for calculating. We're asked to consider the number of significant figures. Looking over some basic ideas that will help you with significant figures, I'm going to offer you the Atlantic-Pacific rule. Essentially what the Atlantic-Pacific rule says is that if you think of the numbers you're analyzing as a map of the United States, and you only have to determine whether or not there's a decimal present. If there's a decimal present, then you begin your analysis in the Pacific side of the number. And if there is no decimal absent, you'll begin your analysis on the Atlantic side. And what you do is you count the number of non-zero digits and any zeros that may be involved in the number until you hit the last non-zero digit. So if there is a decimal, we would start on the left side of our number, counting all the non-zero digits and all the following zeros. If there is no decimal, we would start on the right-hand side of our number. We would count all the numbers until we got to the last non-zero digit. So those are the basic rules for analyzing the numbers. So now we'll look at the 2 numbers in our question. 80.01. There is a decimal. We start on the Pacific side, so there's 1, 2, 3, 4 values in that number. On the other number, it's 2.70. Decimal's present, so we count 1, 2, 3 significant figures. So what is it going to be, 3 or 4? The answer to this question, because we're going to be doing a calculation here that involves either multiplication or division, the answer to the calculation must reflect the smallest number of significant figures available. And since that's 3, we're going to answer with 3 significant figures. Question number 39. Given 4 particle models, here they are, Model 1, Model 2, Model 3, Model 4, and the particle models are made up of atoms of 3 different elements, T, X, and Z. Which 2 models can be classified as elements? Recall that an element is a pure substance, and therefore all of its atoms must be of the same type. So let's analyze our diagrams. Diagram number 1, we have all 3 different types of elements present, so that is not a pure substance. Diagram 2, we have only 2 element X particles here, so that one qualifies. Diagram number 3, I have 4 atoms that are all the same type, so that qualifies. And diagram number 4, I have 2 different types of elements here. I have a couple of T's and I also have a Z, so that one doesn't work. So our answer is 2 and 3. That's reflected in choice number 3. Question 40. After being thoroughly stirred at 10 degrees Celsius, which mixture is heterogeneous? To be a heterogeneous mixture, we're going to need to see particles that are not dissolved. In other words, we have to be beyond saturated in our solution. In all 4 cases, we're putting the same amount of solute into the same amount of water. What varies is the salt being used as the solute. We're going to refer to Table G, the solubility curves at standard pressure. I've highlighted all 4 of the salts, and I've also located with a purple X the position at which 10 degrees Celsius and 25 grams of solute intersect. So the only thing we have to do now is figure out which one of these solubility curves is actually a saturated solution at a position below where that purple X is. Checking the first one, the sodium nitrate. Sodium nitrate intersects 10 degrees at 80 grams. So that solution is going to be unsaturated, could still hold a considerably large amount of solute. Potassium nitrate. Here we go. This is our winner. Our solubility curve comes in below the purple X, meaning that we've put some extra solute in there which would not dissolve and therefore give us a heterogeneous mixture. Just double checking our other 2 potential answers, potassium chloride and sodium chloride both give us positions that are above the purple X when we consider them on Table G. So our answer is going to be related to the potassium nitrate. That's answer number 2. Question 41. Which 2 compounds are electrolytes? Electrolytes are compounds that produce ions in solution, and that would include acids, bases, and salts. Bear in mind that there's one type of acid, the organic acids, which are characterized by the carboxyl group being on the end of their structure. That's represented by the symbol COOH in a formula. So I'm looking through the potential answers for anything that has a COOH or anything that ends with OH that is not organic. Those would be bases. And we've isolated answer number 1 as being the only combination of compounds that are both electrolytes. Question number 42. Which statement explains why a carbon dioxide molecule is nonpolar? So we're talking about molecular polarity here. Molecular polarity is related to the shape of the molecule that is formed. I have a graphic here that shows several different molecules. Here's the carbon dioxide molecule right here. You can see that the carbon dioxide molecule is very symmetrical. It has an even charge distribution because the oxygen spread out along a 180-degree bonding angle, so that the unequal sharing of electrons happens to the same degree in both directions, left and right, with this molecule. So generally speaking, the symmetrical molecules are nonpolar. So go back to our potential answers here. The molecule has an asymmetrical distribution of charge? No. The molecule has a symmetrical distribution of charge. That's why it's nonpolar. Answers 1 and 2 don't really have a lot to do with whether this is a molecule that's polar or nonpolar. So we're going to stick with answer number 3 and move on. Question number 43. Which temperature change indicates an increase in the average kinetic energy of the molecules in a sample? An increase in the average kinetic energy means we're looking for an increase in the actual temperature. The problem with our 4 answers is that we have temperature presented to us in 2 different temperature units, Celsius and Kelvin in each case. So in order to compare the temperatures to see which one shows an increase, we're going to have to convert the temperatures. Table T gives us the key to understanding how to convert the temperatures. If you want Kelvin temperatures, all you need to do is add 273 to the existing Celsius temperature, and you'll have the Kelvin temperature. I've done that for all of the conversions necessary in this problem. In response number 1, 15 degrees Celsius converted to Kelvin would result in 288. Now you can see 288 changing to 298 is an increase in temperature. There's no need to go any further. If you do, you'll find that all the other temperature changes are a decrease. Question 44. Given the particle diagram, and here is our lovely particle diagram here, where an atom is represented by a dot, and you can see that all the dots are clustered together in a very organized pattern. Which substance at STP can be represented by this particle diagram? What you're supposed to gather from this particle diagram is that the substance we're looking for is a solid. Refer to what a particle diagram is showing us here. Here are particles arranged in a solid. Here's an example of a liquid, and the gaseous material shows the particles widespread. So if we locate our 4 potential answers on a periodic table, and here they are highlighted with a little purple mark. Here's the hydrogen, the magnesium, the nitrogen, and the krypton. We see that only one of those, that would be the magnesium, is located in a position on the periodic table where we would expect to find a solid material. So our answer is going to be magnesium. That's the only one of the 4 compounds listed that would actually be a solid at STP conditions. You could also use table S and look up the boiling points of these and the freezing points and whatnot, but having a clear understanding of their positions on a periodic table is a much quicker way to answer the question. Question 45. Which type of equilibrium exists in a sealed flask containing bromine in the liquid phase and bromine in the gaseous phase at 298 Kelvin and 1 atmosphere? We're really asked to analyze 2 things here: the difference between static or dynamic, and the difference between a phase or a solution equilibrium. So let's take a look at the dynamic versus static first. A dynamic equilibrium is one that has constant movement of reactant to product and product to reactant. And that's the kind of system that we're looking at when we're dealing with a equilibrium system. It's not static. Static means that nothing's happening. Well, that's not how equilibriums work. In an equilibrium system, you have the reaction moving in both the forward and reverse direction at the same time. So we're dealing with a dynamic system. Now, phase versus solution. In a phase equilibrium, you have 2 phases of the same material present, and we go back and forth between them. That's exactly what we have here. We have bromine as a liquid, bromine as a gas. So this is going to be a phase equilibrium system. If it were a solution equilibrium system, we'd have a substance going between solid and aqueous, dissolved and undissolved. So we're going to go with answer number 3 for question number 45. Question 46. What are the products when potassium hydroxide reacts with hydrochloric acid? What's being described here is a typical neutralization reaction. A neutralization reaction involves acids being added to bases to produce salt and water. In this case, since our acid is hydrochloric acid and the base is potassium hydroxide, we know we're going to get the water and some type of salt, which will include potassium ions and chloride ions, which can be written as KCl. Aqueous means it remains dissolved in the water. So we're looking for the salt, potassium chloride, and water as a product, and that is answer number 3. Number 47. In a titration, 20 milliliters of a 0.15 molar sodium hydroxide solution exactly neutralizes 24 milliliters of an HCl aqueous solution, that's hydrochloric acid. What is the concentration of the hydrochloric acid solution? This is a typical titration calculation, so we'll use the equation. Molarity of the acid times volume of the acid equals molarity of the base times the volume of the base. Hydrochloric acid is our acid, and sodium hydroxide being our base. Now we transfer information from the question. This 20 milliliters is the base, so that's going to go where the volume of the base is, 20, and the concentration of our base is known to be 0.15. And then we also know that we're using 24 milliliters of the acid, so that's going to go where the volume of the acid is, and we'll be solving for X. So it's 0.15 times 20, and then we can divide both sides by 24, and we'll get our answer where X equals 0.125 molar. Answer number 1. Number 48. What fraction of a strontium-90 sample remains unchanged after 87.3 years? To answer this question, we need to know the half-life of strontium-90, which we get from table N. It's 29.1 years. With that value, we can now determine from the 87.3 years how many times a half-life has actually taken place. That fraction is little t, the total elapsed time, or 87.3 years, divided by big T, the half-life, 29.1 years. And that fraction comes out to equal 3. So the number of half-lives is 3, n equals 3. This little fraction is going to give us the answer. The fraction of your original sample remaining is always equal to 1/2 raised to the power that's equal to the number of half-lives gone by, which can be rewritten as 1/2 to the n. In this case, 1/2 to the n is the same as 1/2 to the third power, which equals 1/8. That's going to be answer number 4. So we expect to see 1/8 of our original sample. Another way to do half-life problems is to consider that if you start with a value of 1, meaning in the entire sample, and you consider no half-lives have yet occurred, after 1 half-life you will have 1/2 of the sample remaining. 2 half-lives brings you to 1/4, 3 half-lives brings you to 1/8, and so on. In this particular example, we would have been done after 3 half-lives. Number 49. Which potential energy diagram represents the change in potential energy that occurs when a catalyst is added to the chemical reaction? Let's take a look at what happens when a catalyst is added to a reaction. This potential energy diagram has a certain starting point and a certain ending point. The catalyst cannot affect the starting point or the end point. What the catalyst does is it speeds up the reaction in both the forward and reverse directions by lowering the activation energy. Lowering the activation energy means that instead of having to go all the way up to the top of this curve, we're going to have a top to the curve that's a little bit lower. So we're going to start in the same place, go to a height of a curve that's a little bit lower than it was, and when we come back down, we're going to end in the same place. That matches graph number 2 very exactly. The others are just decoys. And question number 50. Which balanced equation represents a spontaneous radioactive decay? Recall that a spontaneous radioactive decay is a natural decay event, so we're looking for the production of either an alpha, a beta, or a positron particle as one of your products. The first equation they offer us is not even a nuclear reaction because we don't really have any transmutations taking place. The second one is nuclear. We're changing nitrogen to carbon, but this is done artificially by colliding it with a neutron, so that's artificial transmutation. Your third reaction, again, not a nuclear equation. So that leaves us with number 4, which shows a carbon-14 atom spontaneously decaying to form nitrogen-14 and a beta particle. Answer is number 4. And that concludes Part B-1 on the January 2015 Chemistry Regents exam. Look for additional videos for Parts A, B2, and C of this exam. Again, thanks for watching. You can access additional videos and materials for this and other chemistry exams at alchemtutor.com. For questions, comments, or permissions, please contact me at my email address, asnyder@alchemtutor.com. If you have interest in contracting tutorial services, you can also contact me through the website at alchemtutor.com.